analysis. Bridget. Dick Show just came in. Is Austin here? Sally just came in. Jerry just came in. Toussaint just came in. Edward's not here, right? And James just came in. And no Charlotte. Okay, so I have Amanda, Alexis, Bridget, Austin, Edward, and Charlotte that aren't here right now. A couple of announcements here. First, well, they both have to do with the bookstore. The bookstore can purchase paper copies of the textbook. We've not seen one, so we can't verify what the quality is, but they told me that it's high quality printing, full color on good paper for $40. So if you would like one, contact the bookstore on that. Second one, if you purchased a new clicker, I know I talked to one student already, but for other people who have purchased a new clicker, you should take it to the bookstore and replace it. The replacement is free. The email says you don't have to have the box, just take it over there. You may be happy with it, but it doesn't have as much functionality as what you paid for. And we would like to have the ones with more functionality so you can sell it back to the bookstore and then they can sell it to another person instead of it being yours for life. So, those are my two announcements. Any questions about the announcements? Okay, then we shall move on. I'm not going to ask you. Question, Chad?
Well, I was just going to ask you when the test will be graded.
I hope to get a lot of it graded tomorrow. I cannot make a promise on when it will be completed, but I plan on spending all of my free time tomorrow, which is not as big as I would wish it was. Okay, in 1687, sometime after the Black Plague, Newton wrote his seminal treatise on physics, which we usually just call Principia Mathematica. Full name there, Philosophiae Naturalis Principia Mathematica. Natural philosophy, principles, and math, I suppose, would be an English translation of that. And that's, where he outlined his findings in science, and that lays the groundwork for most of what we are doing at this point in physics. So it's always good to make sure we know a little about Newton. We've already seen free body diagrams on Flip Friday, but I haven't talked about them. And even though the theory in Flip Friday is that's where you are teaching yourself, I still feel I need to go over the topics that you're teaching yourself. So first the figure on the left, then the figure on the right. The figure on the left shows two people pushing a third. These are ice skaters, apparently. That's what the arcs are supposed to be on the ice. You might or might not know that figure skating is figure skating because part of figure skating used to be the elementary figures. You had to do something like stand on one leg and make a perfect figure eight. And then, they did things like that and they were great on that. And it was somewhere like 6 years ago where they got rid of the compulsory figures because nobody liked them. And nobody watched them. In the Olympics, every now and then they show, and here was a picture yesterday of compulsory figures, and you have an empty room with judges standing there and going, yep, that's an 8. Anyway, so these two young ladies are pushing a third young lady at right angles to each other. And so we want to calculate the total force. Why do we want to calculate the total force? The reason for everything I'm going through today basically is so we can use Newton's second law. So we start drawing the figure here so we have a picture in our head what's going on. We draw the force arrows so we can use them in Newton's second law. Now this over here is the technical free body diagram. I was telling somebody else this earlier. Right now I'm letting the textbook show you how to make the technical free body diagram, but usually I only use, personally, this one here. This one here has all the information. It just has some other information. So what is the free body diagram? You've seen a lot of it. You could probably all answer with some semblance of correctness. But to put it in the simplest form, the free body diagram is showing all of the forces acting on the object you're interested in. So in this case, the object I'm interested in is the figure skater wearing the blue top. And so I'm showing only the forces acting on the figure skater in the blue top. So for instance, there are other forces. According to Newton's third law, for every action there's an equal opposite reaction. So if I push on Luke, he's pushing back on me. And the force he's pushing back on me is exactly equal to the force I'm pushing on him. So if we look at this, we could say, well, now, there's a force of the lady in blue pushing back like that, and a force of the lady in blue pushing back like that. My arrows should be the same length as the ones that are there, but I ran into F's in both cases, so I stopped them. Those arrows aren't shown. Why are they not shown, Alexis? They're correctly not shown.
I don't know, actually.
I mean, I said your name right, didn't I?
You did.
That's why I chose you, because I'm working on the name still. Yeah. Okay, anyone, why are the green ones not on there? Because they're what? Not that they're wide. No. Okay, yeah, I misheard you the first time. It's not because they're implied. They're not there because they shouldn't be there, not just because they're implied to be there. Haley?
Because the two other people are not the system you're looking at?
Because the two other people are not the system I'm looking at. I want to look at the forces acting on the lady in the blue top. And those two forces are acting on, one on the lady on the left, one on the lady below. Yes, Diksha?
So the green arrows you're saying is the forces that are acting on the pink shirted lady?
Correct.
Okay.
And so that's why those are not part of the diagram. And those should never, ever make it to a free body diagram. I can draw a diagram and show forces acting on multiple objects, but the free body diagram must be only the forces acting on the object I'm interested in. So here we have just those two forces. And then once we have those two forces, you say, why did I add those two forces together? And the answer is so I can use them in Newton's second law. So we went through an activity where I had you very specifically say the x components and the y components, and you broke all of your forces into x part and y part. The reason being, Newton's second law, just like our kinematic equations, has independence of motion. The forces in the x direction can be treated independently of the forces in the y direction. I'll get you. And then we use Newton's second law in each of the directions. So we started with this free body diagram showing the pictures so we could break the forces into components so we could apply Newton's second law in each of the component directions. But it's a very simple reasoning for this. It's not, and that's another step I just have to do. It's part of the process of getting to the answer. What was your question, Cassie?
Yeah, it's a free body diagram. Just a simple question. How come the arrows don't point towards the dot if that's where the force is being applied to? If that's representing the
Okay. Why don't the arrows point toward the dot? She's talking about the one in blue, the one I circled in blue. You can actually put them going in or out. Nobody really cares.
Okay.
You just have to show the forces acting on that object.
So it'd be fine either way.
It'd be fine either way.
Okay.
Yes?
Well, wouldn't directions still matter though?
Wouldn't what?
You couldn't just put the arrow on the other side.
Well, I could put the arrow like that. It still has to be pointing up, and I have to have something that indicates acting on the object there. But I could have done it either way. Now, notice this force here, the force total, that didn't show up in the free body diagram, even though it was shown in their diagram here. Why didn't the force total show up in the free body diagram?
Isn't it not an actual force?
Yeah, it's not an actual force. It's what we get when we add them all up. And so that's not going to show up. It will be the same thing next week, I think, when we get to circular motion, we talk about the centripetal force. The centripetal force is actually the sum of the forces toward the center. And since it's the sum of the forces toward the center, it's not an actual force, it's the sum of forces. And so it never shows up on a free body diagram. Good answer. Okay, in tribute to last week's Apple extravaganza, I actually prepared this for a week ago today when it was the day of Apple's big announcement that, hey, look, we've provided slightly different but the same phones. I have a picture here of Isaac Newton. I like to put attribution when I can, but I could not find the origin of this figure. It might be from this sohagroup.com because I saw that URL on about 5 versions of the picture, but I saw lots of other URLs people put on the picture as well. But it's an interesting picture. Einstein sitting there with Apple falling on his head saying, oh my goodness. Tweet, tweet. Okay. What was this about? My sneezes are about 100 decibels louder than hers. Well, what's the interest with an apple falling? I talked about it before, didn't I?
Because it just fell.
No?
And nothing.
Yeah, it fell and there was nothing pushing on it. And so Newton said, hey, that apple, if it was up here stationary in the tree and then it fell and it kept falling down and hit me on the head, there must have been a force that was making it fall. That was a really good contrast color choice. Here's where magenta works, I think. There must have been a force pulling it down. And what's the name of that force? Gravity. Now, Newton had his second law. Second law came about just about the time, I'm sweating so much I had to take that out of my pocket. I don't like to get soaked. He had come up with his second law, and so he says, okay, we have a force of gravity. The sum of the forces on this thing has to be equal to its mass times the acceleration. So if it's the force of gravity is the only force, assuming, of course, no air resistance. And that's equal to the mass times, what's the acceleration of something falling in free fall? G. And so just applying Newton's second law in one step, you come to the relationship that the force of gravity must be mass multiplied by gravity, m times g. Now, once again, nomenclature. When I show things from the textbook, I'm going ahead and leaving them with the textbook's nomenclature for the forces. They use W for the force of gravity. W standing for weight. Because weight is traditionally the force of gravity acting on an object. I always use F sub G personally because if it says F, then I know that's a force, not to be confused with anything else. We have W is equal to work coming up. And so if I have a problem, W work is equal to W weight times, distance something moves. That's going to be really confusing, having W equals WD. But if I do work is equal to force of gravity D, then I don't have the confusion if I have the F sub G. So that's the big reason why I have all my forces have a capital F and then a lower or a subscript, whatever they are. So I put F sub G, and I want people to be clear with their own thinking. If you are clear using W and shifting from W meaning one thing to another thing in the same problem, then you're probably more gifted than me, but go for it. Okay, our first clicker question. What was revolutionary about Newton's apple? Not to be confused with the apple Newton. And you can answer now. interesting. I have another clicker today that I didn't have before. That's yours, James? Oh, did you change it already? Yeah. Okay. Thank you. All right, so what we got was 0, 1, 19, 1. This is a place where I must have taken a swing and a miss, because the answer is not to show that gravity is a force. The key was, and somebody said, Lindsay said, Lindsay, you better be the one person that got this right. The key was that as it was falling, there was a force acting on it. There was nothing touching it. And so there was a force acting at a distance. Prior to this, it was thought that pretty much I had to push on something. You know, I said I had to, if I push on Luke, he'll push back. If I push on Chad, I can put a force. But I can't. I used exactly the same example yesterday. If I push on Chad's phone to make him stop playing his game, that's making a direct contact force. But this was a force at a distance. And that's what was really key, that it was a force at a distance. Now, Newton took this and looked at other things such as the moon, which is why I talked about this yesterday in astronomy. And he said, okay, or yesterday, I guess it was Monday. I have the moon up here in the sky. Why does the moon not fall down and hit me on the head like the apple did? Forces.
It is falling.
Okay, it is falling. Right, I did not talk about that with this class, right? It gets confusing when you talk about the same topic as multiple classes. We haven't gone through this, right? Okay. Okay, so it is falling, is what Ryan said. But it's not falling and hitting me on the head. And of course, I don't want to hit me on the head, so I'm falling and dropping in front. So how can it be falling and not falling and hitting me? It's not getting any closer to us. In fact, it's moving about 1/4 of an inch away from us every year.
It's moving really fast. So as it falls, you can imagine if you threw a ball and it creates an arc. That arc is a radius around the Earth. So it's continually falling.
Okay, Ryan is correct. For everyone who didn't hear, here's what Newton basically said. He said, okay, so I have a ball rolls off the table, and gravity makes it fall down. And since I rolled it off nice and slow, it fell close to the desk. But if I roll it faster, it hits the ground farther away. And so if I roll it really, really fast, it'll go a really large distance before it falls the meter or so and hits the ground. Now the key here is, we know that the Earth is shaped like a sphere, right? I just realized, I've got the recorder way up here. No one's going to hear me on the recording. It's okay. I got it. And it's white, so it didn't hurt. Where was I? Yes. Everybody knew the Earth was a sphere. In fact, when did we come to the conclusion, we as humans, as educated humans, when did the educated humans come to the conclusion that the Earth was a sphere? Cassie says recently. Okay, that's something said around 1500s. A long time ago. Well, Diksha clearly is in strong opposition to you, Cassie, recently versus a long time ago.
I'm just saying.
Michael?
Wasn't there some kind of like Greek mathematician who like figured that out?
Yeah. Yeah. Around 300, 400 years before Christ is when it was conclusively determined that the Earth was a sphere. Yeah, see, Diksha's right, a long time ago. What was that? Okay, so it's been a long time that we've known that, but then that always begs the question, what the heck was going on in 1492, 1493, Great by Sea, 1494, the Golden Shore, I don't know, 1492 really. What was going on when Columbus sailed the ocean blue? What did the whole...
Trying to get to China and avoid having to pay the fees on the Silk Road.
India, wasn't it? Not China.
It's one of these.
he was going he was going for an alternate route. And so many people have heard the story that Columbus proposed, instead of being flat, that the earth was a sphere, and so you could go this way and get there. But everybody knew that the earth was a sphere. That was no mystery. Columbus just forgot that it was very well known already what the diameter of the earth was. The diameter of the earth was determined well before the birth of Christ. And Columbus apparently wasn't educated enough to be aware of that, and he thought that the earth was small and it would be a short distance going the other direction to get to India. And it wasn't until the 1800s when some dude named Washington Irving wrote a book about it that he made up the story that people thought the earth was flat, and Columbus said, no, it's a sphere. Okay, so just had to get that on there. Newton said, because the earth is a sphere, if that ball goes fast enough, it will curve toward the earth, but never hit the earth because the earth is curving away from it. Now, if we go to Newton's laws, the first law says an object in motion stays in constant motion unless a force acts on it. That means constant motion means constant velocity. So an object will have constant velocity, which means if there is no force on the moon, what would it do? Go straight line, we'd say bye-bye. It would not go away from us. It's going around a circle. If you turn off the force, it just keep going in a straight line. But that gets it a lot farther. It's just not going directly away. So the moon would go in a straight line. We call the propensity of it to travel in a straight line at constant velocity inertia. So Newton's first law is called the law of inertia. And inertia is measured in kilograms. Mass is a measurement of the inertia of an object. The more mass it has, the more propensity it has to go in a straight velocity. Straight velocity, that makes sense. Go in a straight path with a constant speed, constant velocity. And Newton's second law identifies the relationship between the acceleration, which is the rate of velocity change, and the force that makes it curve. And so, using his second law, he was able to, once he formulated the law of universal gravitation, explain what's going on with the moon. So we have the law of universal gravitation that's not in the textbook yet, but Newton determined that the force of gravity between any two objects was always attractive. So I know it's a little bit silly, but I always take a pair of students, Chad and Jaron, and there is a force of gravity acting between the two, and since the force of gravity is always attractive, there's a force that's pulling Chad to Jaron, a force that's pulling Jaron toward Chad. There's also a force that's pulling both Chad and Jaron to the three young ladies behind them, and so on. There are forces attracting all of us to each other, gravitational forces. And that force of gravity, Newton determined was proportional. Did you have a question? Somebody? No. Newton determined that force of gravity is proportional to the product of the masses of the two objects. So it's proportional to mass 1 times mass 2, and inversely proportional to the separation squared. So R here is the separation. More specifically, it's the separation from the center of mass to the center of mass. And notice I said proportional. So we have a constant of proportionality, capital G, where G is just constant. So that's the actual form of the force of gravity. Now, just on the previous slide, I wrote an equation for the force of gravity. That wasn't that. I wrote force of gravity equals mg. You notice also as a habit I use the lowercase g when I'm using one equation and capital G when I'm using the other. That's a way for me to distinguish just which form of the equation I'm using, but it's really minor. How can these both be true? They're both true. Well, we set them equal to each other. What are we attracted to? The Earth. So mass of the Earth is one object. The mass of me is the other. How far are we from the center of the Earth? In word, not in number. A ways. The radius of the Earth. That's the distance from the center of the Earth to us. So over the radius of the earth squared. So if these are equal to each other, I have an m here and an m here. So the thing that's not the m must be equal. So we have g, the acceleration of gravity, is capital G times the mass of the earth over the radius of the earth squared. So we can use g only if we are close to the surface of the earth. Now if you're 10 meters above the surface of the earth, the radius of the earth is far, far bigger than 10 meters. So we don't worry about the change in 10 meters or even 100 meters. But if you get significantly farther away from the surface of the earth, then it's going to make a difference. So for instance, if you go to the top of Pikes Peak, you're significantly farther from the center of the earth than you are if you're here in Lincoln. So the acceleration of gravity, if r gets bigger, what happens to g? It gets smaller. So the acceleration of gravity is smaller at Pikes Peak than it is here. Now, it's not a lot smaller because that's still a small fraction of the radius of the earth that you went up. But it is measurably smaller at Pikes Peak than it is here. Which makes me happy because if I go from here to Pikes Peak, since g goes down, I will have lost weight. I won't have lost any mass. Mass is a measurement of what makes me up, how much of me there is. But I will have at least lost weight. The scale will say you weigh less. And now, just a little historical note, just so people are aware of these things. The Cyan Organizer was the first PDA, Personal Digital Assistant, because the Apple Newton, released in 1984, which is an awesome year because it's the year I graduated from high school. The Apple Newton was the first device, though, called a PDA. It was announced in 92 and released in 93. The IBM Simon in 1994 was the first PDA with full cell phone features, and we've come to call those smartphones. So my smartphone here would be a PDA. It is the descendant of the Apple Newton, but the Apple Newton was a pretty big flop in reality, but it helped to start a revolution that Apple has capitalized on, so they make over 90% of the profits made on selling cell phones today. Okay. Was that an important comment? No. Okay. Moving to a new force, spring forces. A spring is something that is made out of a material that you can bend and that is elastic. Elastic means you deform it and it comes back to where it was. Plastic means you deform it and it stays deformed. And so springs are made out of something elastic. And I want to have a student come up and do a quick experiment for us. So who wants to come up and do this quick experiment? Reagan, you can't just go volunteering people. It does, really. All right. Thank you, sir. Now, what you're going to do is really, really simple. And, for the sake of everyone else, I'll try to remember how I video record things. So come on over here. And this one here. And what I'm going to have you do is first take a pen and mark a line at the bottom edge of where that is. You kind of have to visualize and see it. Let's see. Oh, crap. Got to make a change. No, it's not you. I've got to turn off that part.
Right here, it looks great.
Yeah. Okay. We're going to trust you. Now, put one of these 20... okay, mark it again. Then put one of those 20-gram masses on. Dude, just eyeball it from where you are. Don't look up the screen. Okay, now put a 20-gram mass on and repeat. Yeah, it'll be a while if you let it swing. Okay, repeat. And then you can give your parents the link and they can watch you in action in physics class.
I have difficulty drawing lines.
You don't want to admit that to your parents, do you?
Yes.
It's pretty exciting stuff, isn't it, everyone? Oh, he. Okay, now that he's done with that, now we grab a meter stick and we take a picture of all the excited students out there and measure right beside each one the position. Just make the first one at 0. You can just completely move this.
Oh, nifty, thank you.
Yeah. So who's paying attention while you're doing this? Yeah. Nice. Okay. Okay, that's it. Thank you, sir.
Yeah.
So let's... There was a problem. Okay. I don't care. There's a problem. Here is the results that he got. 0, 6.5, 13, 18.8, and 25.5. Can you see a rough pattern to that?
Sorry, my measurements wrong.
Okay. 11:01. Look at the time. Oh, look at the time. Okay, I am going to try this with a different camera app that should not fail when I try to save the picture. Notice it was all in focus and then it goes blurry at the very end. Okay, so here are his measurements. Now, if we take those measurements, and if I find where to put my stylus. Awesome. I don't even have it set up so I can write with my finger. Seriously, where did I put my stylus? There it is. It fell in the sink. Okay, so if we look at these, we can make a graph or a table first with the force of gravity and the amount that it's stretched. Now, I said the force of gravity. I actually am going to use force of gravity at first, and then I'm going to change it. What are the units for the force of gravity? What? Newtons. And the units for position? Okay, meters. Now, we're going to have, not meters, in this case, centimeters. And we're going to have some uncertainty. So what would your uncertainty be on this, Reagan?
Oh, say centimeter and a half to 3 centimeters. Just ballpark figure.
I'll go with a half. Because that would be ridiculously bad.
Yeah, well, 18.8, that's messed up.
Okay, so we'll put in the distances here.
It's 18.8, I wrote it. That really says 15, Reagan.
I thought it said 15.2 when I was looking at the recording, but then when I look at this, I see.
Close.
Yeah.
You saw it. That's okay.
Okay, so we have those values for the distance. What did he not do? He forgot to put that 0. That's significant. It wasn't 13.4, right?
Yeah, it was understood.
It was not understood. If you put just 13, it's understood that you weren't as careful on that one.
Huh?
If you put just 13, it's understood that you weren't as careful. That's what that means.
Yeah.
He actually isn't arguing with that.
Plus or minus a centimeter.
Okay, the force of gravity. Each one of those little masses was 20 grams. So how do I go from 20 grams to the force of gravity? What's the equation? mg. What units do I need mass in? Kilograms. So that's 0.020 kilograms times 9.80 meters per second squared. And of course, 2 times 9.8 is 19.6. And then you move the decimal place over from 19.62, and that's 0.196 newtons. And then the next one was 2 times that, so 0.392. And then add those two together for the next one. 8. And so there we have our forces. Now with those forces and positions, it's very useful to make a graph. I'm going to put my graph right on top of the, actually, I'm going to put a white background on the picture and do it on that. Darn it. I was close. Filled rectangle would have worked better. All right, so on that I shall put my graph. And we're good to go. What do I have on the vertical axis? There's only 2 options. What do you think I should put? Okay, I'm going to put force. Now over here I had the force of gravity. On my spring, I had, if I look at the end of the spring, I had gravity pulling down on it, and there was a force due to the spring pulling up. And so I'm going to actually put this, the force of the spring, in newtons. And on this axis it will be the length it was stretched. Well, I'll just put stretch. Oh, nice call. In units of meter or centimeters. And so then I can plot things out. It goes out to 25, so let's make this 25. And it goes up to 0.784, so we'll actually leave that one at 1. And now I have the basis to graph this baby. It actually would have worked better if I had not put it on the white because I have a grid underneath this. But mistakes of the past. 0.196, this would be 0.2, so 0.196 is about the same, and it was at 0. Or it was, excuse me, 0, 0.196 and 6.5, so about. Next one, 0.392 and 13. Next one, 18.8 and 4. And finally, 0.784. And so that's, to the best of my graphing ability on this, our data. Any disagreements?
When did you put spring force for that? Didn't you calculate it as the force of gravity?
Yes, I did. That's, remember I said we had, if you look at the spring, you have a force of gravity pulling down and a force of the spring pulling back up. And so if it's in equilibrium, I didn't say this part. If it's in equilibrium, the net force is 0. Equilibrium means the net force is 0. And so the acceleration is 0. So when it's stationary, the velocity is not changing, acceleration is 0. So these two had to add up to 0. So I had that's why I made the switch. So now if we look at this, I can draw my best fit line. Now remember, lines need to be best fit. Unfortunately, I can't make a very good best fit line by hand, so I'm going to do something that's a horribly bad procedure. I'm going to start at 0, 0, and then try to make the best fit that goes from there. Now notice I didn't connect the first and last points. I did start at 0, 0 because of the limitation of my being able to draw this. If I had a ruler, I would have tried better. But I have these kind of split. This one's above, this one's below, this one's above, this one's above. You know, that's about as good as I can get to try to match it. But you see that's pretty close to a straight line. And so if that's close to a straight line, then I can find the slope and say that the force, straight line actually works for the force. The force of the spring must be equal to some constant that I get from the slope multiplied by the amount it's stretched. So that's what we had here at the top. The force of the spring is some constant times the amount it's stretched. Now I put a minus sign here. And yes, I put it there. I don't think the book had it in this graphic. That minus sign is actually important because when you elongate the spring, it pulls it back to its natural position. When you compress it, it'll push back out. Now this spring you couldn't compress, you could only stretch it. But some springs you can compress or stretch, and it works the same either direction, always trying to restore to its equilibrium length. And so this minus sign tells us that it's restoring. You see right here it has the word restore. This man is pulling out, and the spring is trying to restore back to the unstretched length. So that's another kind of force for us to deal with. Where do you see things like this? You go to the supermarket, you get your bag, you fill it with dark chocolate covered almonds. You know, get the almonds because we got 40 acres of almonds. You wrap it up and you put it on that little scale, and traditionally you had, now the new ones aren't this way, but traditionally you just had a spring inside a covered thing so you don't see it that stretches, and as it goes down it just pushes an indicator, and that indicator tells you what the weight is. Right? That's the basis of the traditional supermarket scale, is using a spring. Why do they use the spring? Because of the linearity. So, all of this to introduce the spring force. Go to our next kind of force, or at least our next kind of force, either that or the next clicker question. Or we freeze. Normal force. We've talked about normal force, but there are some important things we have to make sure we remember about normal force. First, the normal force is the force that keeps an object from going through a surface. So right now Chad has his briefcase sitting here on the desktop. The briefcase has a weight that's pushing down. The table's not letting the briefcase go through it. And so the normal force is the force of the table pushing back up to respond to the briefcase. If you read the textbook, you'll see it talks carefully about what's actually happening. When he puts his briefcase on the tabletop sags, believe it or not. It sags by a minuscule amount for his briefcase. If Chad were standing on it, it would sag a little more. If Chad and I both stood on it, it might sag enough for people to notice. If we all stood on it, it would definitely sag enough to be noticed, if not break. So the normal force is keeping it from going through. And it will be whatever force is necessary to keep something from going through until you get to the failure point where it breaks. What direction is the normal force? It's the direction coming out of the surface, regardless of the direction of the surface. So if I push on the wall, my fist doesn't go through the wall. So the wall must be pushing back to keep my fist from going through. We call that the normal force. And its direction has to be coming out of the wall, which is that direction. So now we have this person with their bow wow chow. In the first picture, the bow wow chow is being held by their hands. It's not sitting on a surface, it's being held by their hands. And we traditionally say, okay, then the force of the hands is lifting it up. The force of gravity is pushing down. And what about force normal? You must say there is no force normal because it's not pushing against the surface. Now, when he or she sets the bow wow chow on the tabletop, now it's sitting on a surface. Now you have a force normal that comes into play, and it's directly out of the tabletop. If this had been rotated, so if, like, let's say the tabletop was like this, I don't know why we would have a table built like this, but let's say we did, and we put the bow wow chow, I chose the same color. We put the bow wow chow on here. What direction is the force of gravity? Force of gravity is straight down. Always straight down because that's how we define the force of gravity. I actually am in the habit of putting force of gravity is equal to mg because I know that it is. What direction is the force normal? Okay. The force normal is perpendicular to that surface. And once again, notice I put Fn for force normal and F sub g for force of gravity. So I know these are both forces. The textbook used W for force of gravity and N for the force normal. So you need to understand both. Use the ones that you feel make more sense to you. Obviously, when I'm grading the exam, I don't mark you off if your symbols don't agree with my symbols, just in case people are worried. Now, we did for Flip Friday something like this, except for it was a young lady going down the slope instead of a man. And so when we put the forces on here, you notice we have the force of gravity coming straight down, the force of friction going up the slope, the normal force going normal to the slope, and then we have to determine what direction am I going to use for my coordinate system. Our traditional coordinate system, x, y, right? On this graph, they have marked a direction parallel to the slope. That's what this means, parallel to the slope. And a direction perpendicular to the slope. There are two reasons here to choose the coordinate system that they're going to choose. So let's look at reasons to choose a certain coordinate system. Now, number one, we know our coordinate system has to be perpendicular, right? We can't have x and y at an angle. So I can't like say, well, I'm going to make vertical my y and down the slope my x. That doesn't work. We need them to be perpendicular. And considerations. Consideration number one. Make one component parallel to acceleration. That is your first priority. If there is an acceleration, make one component parallel to the acceleration. So on the Flip Friday, I asked you, what direction is it accelerating? And you answered down the slope. And so since the acceleration was like this, I said make one of them parallel to that. So if you make one parallel to that, the other one's perpendicular. Second priority. As many forces as possible parallel to a coordinate direction. Now in this case, that turned out to also be true for the selection of having an axis parallel to acceleration, because the friction was parallel to the acceleration, well, anti-parallel, and the normal was perpendicular to it. So friction and normal were both already resolved into components if we chose a tilted system. A third consideration would be make horizontal and vertical. Fourth consideration would be random choice. Of course, you really are done with choices by the time you said, okay, I'm just going to choose horizontal and vertical. Now, of these, horizontal and vertical is not what I'm going to choose. Why not? Yeah, my first priority set it. If my acceleration had been 0, it would have gone to the second priority. If there were multiple choices that would have had the same amount of pre-resolved vectors for force, then I would have gone to 3 and said, is one of those horizontal? If neither of them were horizontal, then I would have said, okay, I'm going to make a random choice. So the choice here was to have x up the slope and y normal to the slope. Now some people might say, why x up the slope? X up the slope because this is what we call a right-hand coordinate system. And you're going to be hard-pressed to find a physics textbook that doesn't use right-hand coordinate systems as much as possible. Right-hand coordinate system means that you go 90 degrees counterclockwise from x to y. And we'll talk about y later. Let us end with a clicker question. Rank the criteria for determining coordinate directions by importance. If I understand how this works correctly, you put the order you see as fit. So for instance, if you thought A, B, C, D was the correct order, you type in A, B, C, D and hit enter. Obviously, A, B, C, D is not the correct answer. I know.
When you send these numbers,
Okay, then it'd be 1, 2, 3, 4. Okay, I'm going to cut it off here in like 3 seconds because class's time is over. So what we had here was 21, 50, 75, 52. This here was indeed the number 1 priority. This one here was number 2, which had a very slight lead over number 3. So at least the way the points were up was, yeah, it was set. So if everybody answered correct, it would be a 3-2 or 4-3-2-1 ratio. All right, I will see you in class on Friday. Remember, there will be a Flip Friday worksheet to bring to class on Friday. And there will be homework due Friday night.
Okay. Oh, thank you. So here's the